Hello everyone. Today I'm just going for teaching the distillation. So distillation is a very common process in petroleum industries and the chemical industries. So generally crude oil can be separated in different components like gases, petrol, naphtha, kerosene, diesel, and bitumen. So as you see in this image, and crude oil is in liquid, and then it is heated at a high temperature. At different temperature range, you will get a different components. Okay, so here today I will tell you about which equation or which method we will use to design this distillation column, and what are the parameters required for the designing of a distillation column. Okay, so we are using the McCabe-Thiele method and the punch and Javert method. These two methods generally we use um, for this distillation. Okay, so the reference books are Mass Transfer Operation Robert E. Trable and Principle of Mass Transfer and Separation Process B.K. Datta. These two books are reference for this distillation. Okay, so the McCabe-Thiele method is developed in 1925, and it is a graphical method to determine the theoretical number of stages required to effect the separation of a binary mixture like McCabe and Smith 1976. This method uses the equilibrium curve diagram to determine the number of theoretical stages required to achieve a desired degree of separation. It assumes constant molar overflow, and this implies that molar heat of vaporization of component are the same, and heat effects are negligible. So what are the information we require for this method? We require the VLE data, feed composition, temperature composition, distillate and bottom composition, and the reflux ratio. Okay, so this is a design for the distillation column. Here you will see there is a stripping section and the rectification section, and here you will see the feed is going in this from the left hand side, and for the anode plate the vapor is going up and the liquid is going down, and in emmet plate the liquid is going down and vapor is going up, and this is a reboiler where you will heating the uh, liquid, and it is going in vapor and then it is going up, and here you will it is a condenser and you are collecting the distillate here, and some are you are sending back reflux is back, and but some are you are collecting here the product. So this is how the distillation column looks. So what are the steps for the determination of the number of theoretical stages by the McCabe-Thiele method? So first you do the equilibrium curve using available data, then the determining of the rectification section and stripping section operating line, and determination of the feed condition, determination of the feed section operating lines, and determination of required reflux ratio, and then you will determination of the stripping section operating line. So these things you just do, and then based on that you can calculate the theoretical number of stages. So this is a full entire column. So if you will do the total material balance, so what will happen? So F equal to D plus W. D is a distillate which you are collecting, and W is going for the bottom you are collecting. So this is, and if you will do the component A balance, because you are this is a binary solution, so component A will do the balance. So in a feed the composition is ZF, and xt is in a distillate, and xw in it. So this will be the component balance, and you can also do the energy balance when if you require the heat in a bottom, so you will add in feed, and then the condensate you are releasing the heat, so in that case you will come in a right hand side. Okay, so now you will see the rectification section so how you will generate the operating line for the rectification section, which is the upper part of the system when you are where you are just acting for the distillate. So this is we have a assumptions that the rectifications and the molar flow rate is constant, L1 L2 is constant. So if you will do the component balance for this part, in this part if you do the in envelope 2, so you will get vapor which is going then up, and the liquid is going down inside the column, and the D is out. So in that case, the L and D will be the in right hand side, and V will be the going upper side. So this is, and then so the reflex ratio will be the L upon D, which is liquid is going in, and then distillate is out. And based if, and if you will do the total balance, so V equal to L plus D, and then you can rearrange this equation with this. You can directly put this reflex ratio in this equation, and then if you will rearrange, so you will get by an another plate the composition of the vapor you can get. And in terms of R, you can write like this. So similarly, you can also do for the stripping section operating line. So you can also do the material balance for component A uh, in this section, and then you will do the total material balance. And in this case, the liquid is going down and vapor is going to go out, and here we are also the distillate is going also out. So these two, vapor and the residue is going down, so it will be in one side, and L will be the liquid will in a left hand side. And so you will do the total material balance, and then you can rearrange in that respect. In a M plus 1 plate, you can easily calculate a vapor composition. And the ratio here we are using the boil up ratio, which is RB. So this is that. So this is the method we can use for the calculating the operating line, and um, in operating line in stripping section. And previously we have shown the rectification line in, and this is an example where you can see the benzene and toluene can be easily separating by this given xy data, and you can draw this equilibrium lines and this operating lines rectification and stripping, and then you can find the boil up ratio whatever required for this question. And this is how you can easily calculate the number of steps and number of theoretical plates for this section. Thank you for this topic.